All right. I think up to this point in the semester, we've sort of just we've danced around the concept of the chemical bond. And we've got enough information out there so that you can actually work problems, but we haven't actually tried to tackle what is a chemical bond. What do we mean by the term chemical bond? That's first question to consider. Second question is, if they form the bonds, if atoms bond with one another, why do they do it? That's an even more important question. And corollary to that is, how do the bonds actually form? Our starting point is Dalton's atomic theory. I mean, and we go a long way from there, but that's where it all began. He laid the foundations for understanding chemical reactions. We had to understand, we had to start digging at what an atom really is in order to determine how they bond together. And we've come a long way. We've gone through Dalton's atomic theory, and we've gone through the nuclear atom, where we have electrons outside. Nucleus is where most of the mass is. And then just in the last chapter, we are we're drawing electronic structures using the 4 principal quantum numbers. And that's where we're at right now. So the simplest definition of a chemical bond is the force, or the forces, if there's a group of them, that hold these groups of atoms together and make them function as a single unit. That's a very general definition. And when we say ionic compounds form from cations and anions electrostatically attracting one another, then we definitely do have to talk about groups of atoms in that case, because those ions attract one another due to their positive and negative charges, and they form a crystal lattice of billions and billions of them. Whereas molecular compounds actually form bonds between atoms, and then that group acts as an independent unit. So the short version is, actually what a professor told me, a member of my PhD committee, when I was talking to him about a particular problem I was having with my research and how I was going to describe what I was doing in my dissertation. And he basically told me that procedure is operationally defined. In other words, it's whatever you say it is. You just have to give them enough detail so that the reader can understand what you did. So the chemical bond is operationally defined at this point. Here's one thing that we do know about chemical bonds. When the bond forms, the energy of the separate parts, whether they be atoms or molecules, the separate parts before, in other words, the reactants. The reactants have a certain level of energy, and the products have a different level of energy. The bonds form, maybe the bonds are broken in this part of the reaction, and then they reform over here. But one thing we do know is that in order for them to form, the energy of the products has to be less than the energy of the reactants, generally speaking. And you can find numerous examples where that won't hold, except when the energy is known. Say if we draw energy here, and the reactants are up here. Say they go like at this level, and then they drop down to that level for this one, then it holds. But sometimes reactions go like this. What we found out is that the products on that side, actually, even though they may be higher here, they do occupy a local minimum. So they may peak out here, but they come down into this trough, which stabilizes them. And the best example I can think of that is the reaction that forms nitroglycerin. We know that nitroglycerin is very unstable. We also know that it packs a lot of energy in those bonds. And when you break the bonds in nitroglycerin, you come down this other side. And all that energy is released. So the way to explain that is nitroglycerin is sitting down here in this trough. And all you need is just to kick it up a little bit to where it goes over the top, and then you get all that energy back. So that was the long way to say that the local minimum of the aggregate is less than, of the aggregate product is less than the local maximum of the aggregate reactants. But what we're trending toward is stability. If you can find a stable point where it's a low energy part, then the molecule will be relatively stable. And that's an operationally defined term. It's stable, but maybe it's stable. The system is trying to obtain the lowest possible energy. And that's actually a concept that comes from thermodynamics. And we'll have to talk about that next semester, if you decide you want to come back. Okay. So we have generally two types of bonds that we've discussed so far: the ionic bond and the covalent bond. The ionic bonds are fairly simple to understand. They are purely electrostatic attractions between a cation and an anion. And we can use what we know of electricity. And this law was proposed and verified by Coulomb. And all it says is that the energy difference between before and after the reaction can be calculated using this constant, right? And then you need to know the magnitude of the charge of one ion and the magnitude of the charge of the other ion, and divide it by the distance between their centers. Okay, this looks a lot like Newton's law of universal gravitation. Only Newton's law is in terms of force. This is in terms of energy. So the farther apart these ions are, the weaker the attraction. And in order to get them, it's best to look at it this way. If you have two ions here, say sodium and chlorine, and they're bonded, they're as close as they can get, and that bond distance for this particular arrangement is 0.276 nanometers. They're very close. Well, how do you get them separated? You have to input energy. Energy has to go in to move them apart, right? So energy in means the value is positive, right, relative to the system. if they come together from a great distance, then energy is going to be given up. And then that same magnitude will have a negative sign. Okay, so that's how we look at it. And that's if you've got a cation and an anion attracting. But you can also do this calculation for opposing charges, positive, positive, and negative, negative. But they won't form bonds, right? So we're only interested in the cation anion story. So it's easy to calculate the amount of energy that you get back from these two ions coming from a distance of infinity down to their bond distance. And that energy you give up is calculated here. So ionic compounds are fairly easy to understand on this basis. And in this case, we calculate that that energy that you get back when the bond forms is minus 8.37 times 10 to the minus 19th joules. It's very small, but these are very small particles. Okay, that's a good point. If the sign is negative, the calculation tells us that the force is attractive. And if the sign is positive, then it's repulsion. And you're not going to get them together unless you push them together. That means you got to put energy in to make them come together. But if they're opposites, then they come together voluntarily and give up energy. Right? So it's a matter of understanding what the particles are. And like I said before, we're only interested in the sodium, the cations and the anions for bonding purposes. The other type of bond you'll get, and that we've discussed, is covalent bond. Covalent bonds are a little more difficult to understand because, I mean, what's the attraction? I mean, why do they form a bond anyway? Well, if we go back to the bond forms because it's more stable than the separate atoms. And we see from this diagram, this electron cloud here, right? And those are not each dot an electron. That cloud is a probability statement about where the electrons may be found. So we find that separate atoms, the electrons are congregated around the nucleus, in the nucleus. As they get closer, they tend to occupy space between them. And once they get to their ideal bonding distance, there is a significant concentration of probabilities for electron location between the nuclei. That's what we call a bond, a covalent bond. So why do they do that? Well, we have to understand a couple of things. One is there are repulsive forces between the protons, the two protons of the hydrogen atom, and the electron that occupy the space around them. Right? Those are repulsive forces. But we also get attractive forces here between the electrons and the protons. So it's really a balancing act. At what distance do you get so much repulsion that you can't get them any closer? And I think I've got, yeah, this diagram illustrates, and it's best to read this diagram not from left to right, but from right to left. These individual atoms have a certain distance between them, right? And the distance between them is decreasing from right to left, right? They're getting closer and closer and closer. And as they get closer, we notice that the potential energy decreases, right? They're starting to form a bond. And they reach this distance, which for the dihydrogen molecule is 0.001 4Nov2022 nanometers. And that's, as Happy Gilmore would say, that's their happy place. That's where they're the most comfortable at lowest energy. If you try to push them closer, then the potential energy goes way up, because you're trying to get those. The electrons are not as repulsive now because they're on the outside of the protons as you try to drive them together. So it takes a lot of energy. That's why when hydrogen atoms or nuclei fuse, they only do it when they're forced. And in the universe in general, that happens in the centers of stars, because the temperatures are extremely high, right? And when you got high temperatures, you got a lot of kinetic energy. Those nuclei are traveling very fast. So when they smash into each other, there's a lot of energy at play driving them together. Plus, at the center of a star, you've got lots of pressure. And the hydrogen nuclei density is very high. So the probability of encountering one another is very high. So all those factors together overcome that repulsive force that they feel for chemical reactions. Now, they get them close enough to where the nuclear forces, and we won't discuss those now, the nuclear forces take over and they actually fuse them together. And then when they do that, they give up a lot of energy, enormous amounts of energy. Okay. There we go. Okay. This is a review of key ideas. Ionic bonding occurs when electrons are transferred, right? We know that. Covalent bonds, electrons are shared. But there are intermediate cases, right, where we get some electrostatic attraction plus some sharing. And we talked about that. I think we talked about that before. Ionic character versus covalent character. Was that in our last? Yeah. Atomic structure and periodicity. I think we talked about that. If not, we're going to talk about it today. But all chemical bonds reside on a continuum between very close to pure ionic character, very close to pure covalent character. So when we have equal sharing of electrons in the bond, then we have a non-polar covalent bond. And that's what you get with two hydrogens, right? Because neither one of them, it has the electronegativity required to draw electrons away from the other one. So it's an equal sharing. That's what we would call a non-polar covalent bond. Polar covalent bond occurs when one of the atoms is more electronegative than the other one, and it draws some electron probability, some electron density away from the other one. And when it does that, it becomes slightly negative and leaves behind slightly positive on the other side. That's a polar covalent bond, but it's still covalent. They still have to share electrons. It's just this side is more equal than that side. Okay, we can actually measure the magnitude of this polarity. The technology is very advanced and probably expensive, but it can be determined what is the polarity of a particular bond. If you have a molecule where there are only two atoms, it works best. But you can measure the polarity of larger molecules. It's more difficult to get at the polarity of the individual bonds. So to investigate that, we need molecules that are formed with just one pair of atoms. So they just put the molecules, in this case, hydrogen fluoride, between two plates and turn on the juice, a direct current, and charge one plate positive and one plate negative, and adjust that charge until and actually they scan through the charge, the voltage. Actually, it's in millivolts, maybe even microvolts. And they scan through it and they watch the trace and they look for signs, and it takes a specialist to do this. They look for signs as they scan through of alignment of the molecules with the electric field that's created between these plates. Okay. Right, we talked about that already. Forces between atoms. Why do atoms form bonds? The aggregate is generally lower in energy than the separate atoms. And they bond by either sharing electrons or transferring electrons. Oh, I do apologize. I've been using a term that I haven't defined yet, electronegativity. Right, we had a periodic table with trends that we had defined: ionization energy, electron affinity, atomic radius, but there's also a periodic trend for electronegativity. All right, so I've got to explain. Hopefully you'll be able to relate what I'm talking to now to what I've already said about electronegativity. The concept of electronegativity was first proposed by Berzelius. He was a Swedish chemist of the early 19th century. And of course, was studied by other chemists as well after his original proposal. So it was an attempt to quantitatively describe the character of a bond based upon the atoms that were being bonded. So what that means is electronegativity, as opposed to, say, ionization energy. Ionization energy can be measured for a single type of atom, an element, separate atoms. Remember, they have to be in the gas phase. We can measure the ionization energy, or we can measure the electron affinity for individual atoms. But electronegativity is based upon the bond itself. So if you have two atoms bonded together, what's the relationship between their tug on the electrons? So that's a fundamental difference between this concept and the previous concepts. Okay. The most commonly used scale for expressing electronegativities was proposed by Linus Pauling in the early 20th century. Now, once we have an idea about the nature of the bond and can quantify, can measure that attractive force, then we can divvy out a value for the individual atoms. But it originally comes from the bonded forms. And Linus Pauling proposed this scale. And I'm going to give you the math for it in a minute, which you don't have to remember. It just illustrates the point. Now, while we're here, talking about Linus Pauling, he didn't receive a Nobel Prize for just this scale of electronegativity. Actually, he's one of the few scientists who come along periodically, and they take all the information that other scientists have gathered and produced and synthesizes it into a coherent story. He wrote a book called The Nature of the Chemical Bond. And the descriptions that he proposed and the support that he provided for his theories won him the Nobel Prize for Chemistry in 1954. He's one of the few Nobel Prize winners who has received 2 Nobel Prizes in 2 different venues. The Nobel Peace Prize in 1962 was awarded to Linus Pauling. Okay, here's the way he calculated his electronegativities. First of all, and it doesn't show it here, but you need to measure the energy of the bond between 2 atoms. Actually measure the actual value of that energy. Then you go take the bond energies of the separate atoms bonded to their like neighbors, right? So if we want to know the expected bond energy of H with X, we need to know the bond energy of H with itself, HH, and X with itself, XX. You add those bond energies together and divide by 2. That would be the expected bond energy of the HX bond. And then you compare that. You compare that to the actual measured bond energy. And that's what we give here as the symbol delta. And if that delta is 0, that means that the expected value is equal to the measured value, and you have a non-polar situation. And that's one example of the non-polar bond. If, however, the X has a greater electronegativity or an attraction for electrons than H, the shared electrons will tend to be closer to the X. And in this case, H is actually hydrogen. So what that tells us is hydrogen is the reference point, bonded with hydrogen. Any other atom bonded with hydrogen is the reference for development of the scale of electronegativities. Okay, so that's enough said about that. When Pauling added his electronegativity scale to the periodic table, we find that fluorine up here in the left-hand corner is the highest number, and the larger the number, the more electronegative. So fluorine gets 4.0. Can't get any higher than that. And down in the lower left-hand corner, cesium or francium, I think that's right, is 0.7. So all the rest of them occur between there. And you'll also notice that the trend in the periodic table is just like ionization energies. Lower left to upper right is increasing. So that means it increases this way and it increases that way. And for similar reasons to the ionization energy. I think we've got a slide on it here in a second. Okay, so electronegativities express the tendency for an atom to draw electron density toward itself while it's in a covalent bond. But we can use that information to draw some conclusions about whether the bond is purely covalent or only has some ionic character or is ionic. And we just need, where do the breaking lines occur? And what I mean by that is, when you have 2 atoms bonded together, and this one has an electronegativity and this one has an electronegativity, just subtract the smaller one from the larger one, and what's the difference? So the difference in electronegativity is what you're looking for. And that value tells you with a chart to go along with it, or a scale, whether the bond is ionic or polar covalent or non-polar covalent. And I think that's coming up here in a second. First, we got this scale, and this is a periodic table with just the electronegativities thrown in. Notice that in general, the increase is from lower left to upper right. But when you get in that, and it works very well for the representative elements, right? The s filling orbitals and the p filling orbitals. But when you get into the d orbitals in here, it tends to go up and then it drops back down again before you get to the p orbitals, and then it goes back up. So the transition elements are less well behaved. Let's put it that way. But those values are known, have been calculated, and they're known. Now, Pauling's system is not the only one, but it seems to be the most widely distributed and relied upon. All right. So if lithium and fluorine react together, which has a stronger attraction for electrons? So you look at where they are on the table. Fluorine's over here, lithium's over here, right? Fluorine, and they're in the same period. So fluorine should be the stronger attractant for electrons. How about fluorine and iodine? Well, in that case, iodine's down here, and they do form a compound, fluorine and iodine. Which one's a stronger attractant? Fluorine again, because it's above iodine. Okay, so there's your general trend, lower left to upper right. And here's the explanation. It's similar to ionization energy. Across the period, the number of protons increases, which increases the effective nuclear charge, which means they're drawing on electrons more strongly. Now, while you are also adding electrons at the same time, that's not the addition of the electrons to go with the protons is not enough to shield the protons from outside influence and attraction to other electrons. Down a group, you see the electronegativity get decreasing because you are adding more protons, but you're adding more electrons in the core, and they are shielding those protons in the nucleus. So their effective nuclear charge decreases. Okay, here's the scale. If you do that subtraction of the electronegativities and you're less than 0.2, then you can be assured that the bond is nonpolar covalent. If you're between 0.3 and 1.2, then, and I didn't put this in there, I should have, between 0.3 and 1.4, if the elements are both nonmetals, then this scale works. It's polar covalent. But, and I believe the breaking point is 1.2. If it's 1.2, if it's above 1.2, and they're metal, non-metal, metal, non-metal, then that's going to be ionic. But if it's between 0.3 and 1.2, it doesn't matter. It has to be polar covalent because of the way the electronegativities are distributed in the periodic table. And then definitely, if it's 1.5 or greater, it has to be ionic. There's no other choice. Okay, let's see if we can arrange these bonds from most to least polar. One thing is we generally don't talk about ionic bonds as polar or anything else. They're just ionic bonds. When we say polar, we're talking about covalent bonds. So we look to see, all right, nitrogen, fluorine, oxygen, fluorine, carbon, fluorine. All right, those are all covalent bonds. So the nice thing about it is the nitrogen and the fluorine, let's see, nitrogen fluorine, oxygen fluorine, and carbon fluorine, they're all bonded to fluorine. So really all we need to do is say the most polar is the one where they're farthest apart on the periodic table. And they're all in the same period. Carbon is farthest to the left. So this one should be the most polar, right? From most to least. So the most polar would be this one. The least polar, since we've got three, if we do the most polar and the least polar, then with the third one fits in the middle. So the closest to fluorine is oxygen, right? So oxygen fluorine is the least polar. And what do we have left over? Nitrogen. So that's the order. And we don't even have to know the electronegativities to determine that. We just need to know the trend in the periodic table. There we go. Carbon, nitrogen, oxygen, fluorine. B is a little more difficult because it's a mix. So we have carbon, fluorine, nitrogen, oxygen, and silicon, fluorine. In this case, we need to make some judgment calls about the distance between them. The farther apart they are, the larger their electronegativities. So the most polar is going to be the one that has the greatest distance between the two atoms. And if you look at our periodic table, we see that, let's see, silicon and fluorine are pretty far apart. Nitrogen and oxygen are right next together. And carbon and fluorine are far apart, but not as far as silicon. Okay, so this one's going in the middle. And the least polar are these two because they're the closest together. And that leaves silicon and fluorine. So they should be in that order of most to least polar. All right, one more on this slide. Chlorine, fluorine, carbon, fluorine, and nitrogen, oxygen. All right, from most to least polar. The least polar, actually that's misleading. Because chlorine and chlorine would be a non-polar, right? So it wouldn't even fit. But indulge me for a moment. The least polar would be this. And then the most polar would be the ones that are furthest apart, which would be carbon and fluorine. And then nitrogen and oxygen will go together because they're right next door to each other. But there's still differences in their electronegativities, whereas there are no differences here. That's why I put them in that arrangement. Oh, wait a minute. I was looking at the wrong ones. This one's right. I'm getting my letters mixed up. boron and chlorine are pretty far apart. Sulfur and chlorine are right next to each other. There you go. So this was a similar situation to that one where you had chlorine with everybody. This one's the least polar. These two are the furthest apart, and this one's kind of in the middle. All right. Which of the following bonds would be the least polar yet still be considered polar covalent? Okay. Now, in this question, we are given the option of excluding those that are ionic and those that are nonpolar. It's got to be polar covalent, which means it's got to be a covalent bond, but it can't be two of the same elements together. So that means we can eliminate oxygen, OO, that one's out. We can eliminate magnesium and oxygen because that's ionic. Magnesium's a metal, oxygen's a nonmetal. So what do we have left? We have CO, we have silicon and oxygen, and we have nitrogen and oxygen. Right? So the least polar is the one where you have the elements closest to one another on the periodic table. Carbon and oxygen are element in between them. Silicon and oxygen further apart. Nitrogen and oxygen right next door. So this one should be the least polar. Oh, now that we have numbers, we probably should use them. So let's do that. Carbon is 2.5 and oxygen is 3.5. So that's 1.0. Silicon is 1.8 and oxygen still 3.5. .7 and nitrogen is 3.0. 0.5. Okay. So our scale says this one's greater than 1.5. So that's considered ionic. Right. So it's not polar covalent. This one is 1.0. So it's kind of in the middle. It's less than 1.4. But this one, let me see. I got to go back to that scale. I'm sorry. Oops. I missed it. Where is it? Okay. I went too fast. Oh, there it is. Okay. So this one is 0.5, which means it's polar covalent, and this one is polar covalent. But the question was, which one was the least polar? It would be this one. So that confirms it. I mean, we reasoned it out before, and now the values confirm it for us. All right, most polar without being considered ionic. The most polar then would be carbon oxygen. All right. That's how you use electronegativities to determine whether the bond, how to classify it. Okay, when we have the bonds that are polar covalent, there's a concept called dipole. It's kind of like talking about a magnet, right? That magnet has poles, south and north pole. If you cut the magnet in half, what do you get? You get two magnets now with north there and south here. Okay, so it's not a perfect analogy, but the dipole refers to a separation of charge. So you got a positive pole and a negative pole. It's not a complete separation of charge. So you would have a slight negative here and a slight positive there. And that delta, the Greek letter delta, the small delta, not the big delta. The big delta is like that. The small delta is used to designate with a charge, either plus or minus, whether there is a charge separation. Okay, so that's the dipole concept. When we actually, another way to say it, you can do it this way. Another way to say it is to put an arrow in there showing what direction the electrons have moved. And we would do it this way. Put an arrow like that and put a plus on the tail end to show that's the positive side, this is the negative side. And that's called a dipole moment. I think that concept is drawn from physics. A moment in physics refers to a direction of force. So you don't have to know that for a test, but I thought it might be interesting. Now, up to this point, we've talked about the polarity of individual bonds. But suppose we have molecules that have more than one bond in them, right? What are you going to do there? I mean, if you only have one bond, say a molecule that's carbon monoxide, right? You can say something about the polarity of the molecule because you know polarity of the bond, right? It's going to be like this. But what if you have more than one? Say you have carbon dioxide. Now, what do you say about the molecule? What's the polarity of the molecule? Well, we know that the polarity of the bond is this way, and the polarity of the bond is that way, right? So, two things you have to know about a molecule before you can say anything about the polarity of the molecule. You have to know polarity of the bonds. If there are no polar bonds in the molecule, then the molecule cannot be polar. But if there are polar bonds in the molecule, then you need to know the geometry of the molecule to say anything about the polarity of the entire molecule. In this case, carbon dioxide is linear like that. This is an equal but opposite dipole moment. On each side, they cancel one another out. This is a non-polar molecule. So you need to know individual bond polarities and the geometry. Right. So if we're looking at water, we see that the dipole moment for individual bonds is toward the oxygen, like this. But they're not opposite one another, right? So they do what we call in physics, we perform a vector addition. So what's the resultant of these two? It goes this way. So the whole molecule is polar in that direction. The oxygen side is slightly negative and the hydrogen sides are slightly positive. There's carbon dioxide only. They're using a single stick when they should have two sticks for the double bond. But the argument is sound. The dipoles cancel one another out and make this molecule nonpolar. Now, if we're going to say something about geometry, we have to have a concept of what are the regular geometric shapes that molecules might use when they arrange their atoms. The linear one we've already talked about. That's a linear. if you have three atoms bound to a central atom, then they tend to space themselves out equally around an equilateral triangle. And that gives the bond angle of 120 degrees, right? Here, if this is an equilateral triangle, and you've got something here, here, and here, something in the middle, then the bond's there, there, and there. So the bond angle is right here. And they're all equal to 120 degrees, right? Because 120, 120, 120, 360, all the way around is 360 degrees. That one's easy to understand. The one where you have four atoms bound to a central atom, the regular shape that's invoked there is the tetrahedron. And remember, whenever you have a hedron, that means it's a three-dimensional object. And the hedron refers to surfaces. So the tetrahedron has four equal surfaces on it. And we would draw it something like this. The tetrahedron would be like that, that, that for the triangular base. And then there's the apex. Like that. Okay. That's the regular shape. That's not the bonds. The bonds would form, there's an atom in the middle somewhere, and then there have to be other atoms here. Or I'm going to show you, it doesn't have to be atoms, it could be electrons. But the shape is tetrahedron, and the bonds form here, 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 and toward the back. Okay. Now the bond angle is, say, between here, down here, and there, like that. And for the tetrahedron, the bond angle is 109.5 degrees. A math teacher could probably show you how that works, but I just memorize. The rest of the bond angles that we're going to discuss make more sense. This one is one that I just memorize it. 109.5 is the bond angle for a tetrahedral shaped molecule. And there are examples, right? Carbon dioxide will show you for the linear. Sulfur trioxide is an example for the triangular shape, the equilateral triangle. And then the tetrahedral shape is carbon tetrachloride is a good example. Methane would be another one, right? CH4. CCl4 also works, right? Used to be dry cleaning fluid, carbon tetrachloride, until OSHA and the EPA got hold of it and said you can't use it anymore because it's too hazardous. Okay, so when these bonds form and stable compounds result, what we notice is that the atoms in the molecule, now we're talking about covalently bound molecules. Actually, you could extend part of this argument to ionic compounds, but we're going to stick with covalence. What we find is that the stable compounds form when each of the atoms has acquired, by sharing, enough electrons to complete its valence shell, and now it looks like a noble gas. And for the second and third period atoms, that means we complete the octet. Remember? Let me erase some of this stuff. Remember how we got the octet? Well, for hydrogen and helium, right, it's the 1s orbital. So hydrogen's only going to have one, helium's going to have two. That's it. So when you talk about hydrogen completing its valence shell, that's a duet. But the octet comes along when you get to principal quantum number 2. Now you have both S's and P's available. And if they're complete, this one has 2 electrons, this one has 6. And that should be neon. Right? There's your octet. This is the valence electrons, right? All the same quantum number, principal quantum number. So this one has 2, that one has 6, total of 8. That's where the octet comes from. But you can also get that when you go to the third period. Now we're going to 3s and 3p. Complete that octet. There you go. So this concept of the octet works very well for second period elements and third period elements. Now remember that the third period does have access to 3Ds, but in order to get to 3Ds, we've got to go through 4S's, and then we get to 3Ds. Right? So, and that happens in the fourth period. So as long as you stay in the third period, you can talk about octets as the target electron configuration for a satisfied atom in a molecule bonded to somebody else. There are exceptions. But we'll cover them as we come to them. Well, I guess we're coming to them now. 10. 10 is known to have predominantly 2+ ions and 4+ ions. So how does it get there? Well, look where 10 is. It's in the fifth period. So it has 5s2 and 5p 4. 2. There we go. Those are its valence electrons. If we lose these two, what's its charge? If we lose these two, then we have Sn2+, right? 2 electrons gone, two protons left over, 2+. If we lose both of them, then we have Sn4+. That explains the predominance of 2+ and 4+ charges for 10. We get the same thing with lead. But now instead of 5, it's 6s and 6p. Okay. What about, let's see, indium or tellurium? Are they going to use them? Bismuth? Bismuth. Okay. Bismuth is in the 6th period. So bismuth is going to have 6s2 and 6p3. So it tends to lose those 3 and make a 3+. But if it loses these 2, it makes a bismuth 5+. Now the ideal, if we're talking about the octet and the electronic configuration that is isoelectronic with a noble gas, we're talking about losing all 5 of them. Because if we do that, let's see, bismuth, back up. Well, actually, we don't look like xenon because we've still got 5d orbitals. So the octet kind of falls apart when you get down into the 4th, 5th, 6th, and below periods. I think there's one more. Yeah. That's thallium. Excuse me. TL is thallium. And it's only got 1 p electron. So it could be a +1. And it has 2 s's, so lose all 3 of them, you get a 3+. Okay. When 2 nonmetals react to form a covalent bond, they share electrons in a way that completes their valence electron configurations. It makes them look like noble gases, usually, and definitely in the 2nd and 3rd period. when a non-metal and a representative group metal, remember how that zigzag ran like that? The representative group metals are over in here. We're talking about those that we just discussed, like tin and lead and thallium and bismuth. They're all metals, but they're in the representative group, which means p orbitals. Well, p orbitals for them, representative group also includes s orbitals for the alkali metals and the alkaline earths. The ions form so that the valence electron configuration of the non-metal achieves the electron configuration of a noble gas. And the metals just, they're happy to give up their electrons. All right. So here's an isoelectronic series. And I think we talked about that a little bit when we drew electronic configurations. This one is based upon neon. And that makes sense because we're talking about trending toward noble gas configurations is one of the driving forces for forming a bond. So there's neon, that's neutral. Sodium, if it wants to look like neon, has to lose an electron. Magnesium has to lose 2. Aluminum has to lose 3. But fluorine needs to gain 1 to look like neon. And oxygen has to gain 2. Those are isoelectronic ions for neon. We're not going to spend a lot of time on this. Just choose an alkaline metal or an alkaline earth, noble gas, and a halogen so that they form an isoelectronic series. Generally, what you do there is you start with a noble gas. And then those others that you pick, say, how many electrons do you have to add or lose from them to look like the noble gas? And you're generally moving to the left of the noble gas on the periodic table, or wrapping down to the beginning of the next period for the metals, and then they lose electrons to achieve the noble gas configuration. There's one, right? Potassium ion, calcium ion, argon, and chloride ion, all isoelectronic. And you'll notice that when we say iso means same. It's a prefix, a Greek prefix that means same. So they're the same electronic configuration, isoelectronic. That means that they have to have the same configuration. And in this case, argon's in the middle. We use the argon configuration to describe the configuration of each of those other ions. Okay, the number of electrons is going to be the same, but the number of protons will always be different. Remember, when you change the number of protons, you change the element. But you can change the number of electrons within reason. Okay, so we've talked about trends in atomic size. We actually didn't talk much about ion radius. We did allude to it a little bit. If you know the size of the neutral atom, you can infer either an increase or a decrease. Right? If the atom has a tendency to attract electrons, like in the non-metal side of the periodic table, then that ion will get bigger because you're adding an electron to the outside. If you're talking about metals, when they lose an electron, they shrink. It just makes sense. We can predict electron configurations now, knowing where the orbitals are being filled, in which group, right? Alkaline metals, alkaline earths are all S's. Transition metals are all D's. They're filling the D orbitals. Inner transitions are filling the F orbitals, right? Lanthanides and actinides. And the far right side are filling all P orbitals. We can predict formulas for ionic compounds because we know what their preferred charge is. Or if we don't, then the naming convention says you have to be told. But there are only a few selections for ionic compounds. We just described 4 of them from the periodic table in the representative element metals. And we can rank covalent bond polarities. We've done that. So what factors influence the stability and the structure of binary ionic compounds? Well, we're going to introduce a concept called lattice energy. So what is lattice energy? Lattice energy is actually the amount of energy that's given up when the bond forms. So what does the bond form from? If we're forming an ionic compound, now we're switching gears a little bit. We've been talking about covalent compounds, and we're sort of giving side glances to the ionic compounds. Now we're gonna step into the deep end of the pool with ionic compounds. Talk about lattice energy. Lattice energy, and I'm going to write the reaction formula in generic form. The lattice energy is when you have a cation. Maybe I should do it this way. Cation is going to be a metal, right? So it's a charged metal, and it has to be in gaseous state, right? Because we don't want any of those extraneous energy drains to influence our data. Gaseous state here, and the anion, gaseous state there. Okay? What happens? Well, when those two come together, you get a solid. Okay? And then you give up energy. It's extremely exothermic. That's the lattice energy. Now, I drew this metal as a +1 charge, but it can be any positive charge, doesn't matter. And then the coefficients would be introduced to balance the charges. Right? So if this is a 2+ and that's a 1, then we need a 2 in front of it. Okay, that's one condition. And then the formula would reflect that. So calcium chloride would be different. It would have Cl- gas with a 2 in front of it, and a Ca with a 2+ charge to give you calcium chloride. And that would be the lattice energy. Okay. There's a word definition for the lattice energy. And the lattice energy can be related to that Coulomb's law, where we have the K as our constant, proportionality constant, they call it. Then we have the charge of the cation and the charge of the anion and the distance between them. And you can calculate the lattice energy. That's one way to calculate it. The other way is to actually do the reactions. And in order to do the reactions, we can't start from this point. It's very difficult to do that. I think it can be done. But in order to calculate the lattice energy, the reaction actually occurs between, well, let's use our example of calcium. Calcium, solid, plus chlorine gas yields calcium chloride, solid. But several things have to happen before you can get to this point, right? Here's this one right here. So the last step in our process is going to be lattice energy. But first we have to do what? We got to turn that metal into a gas. And that's the first step here. You have to, what's the sublimation energy for the solid, for the metal? Right? That's endothermic. You got to put energy in to make it into a gas. Then once it's at the gas state, then we put a little more energy into it, ionization energy, to kick off an electron. Or in this case, we kick off 2 electrons, right? So it would be the the first plus the second ionization energy for this reaction. And then we go to the nonmetal, right? If it's diatomic, like this example, we have to split it. We have to break that bond. So now we have separate atom gases. That's also endothermic. So far, we've been putting energy in and haven't got anything back yet. Then we take the free atom in the gaseous state, and we invoke electron affinity, right? How does that separate gas atom attract electrons? There we get some energy back. And now we form the ion, the chloride ion, from that exothermic process, electron affinity. Now that we've got the separate gas ion for calcium and the separate gas ion for chlorine, they come together. And when they do that, we get the solid ionic compound, and that's your lattice energy. So the last step is very exothermic lattice energy. And that goes from here to here in 5 steps. And this is a graphical representation. It doesn't come out of your book, but there should be something similar to it in either chapter 8 or the beginning of chapter 9. I think probably 8 will have some type of chart like this to show you you're putting energy in and where are you getting it back. And then, of course, the balance is whether the entire reaction is exothermic or endothermic. In this case, I'd be willing to bet it's exothermic overall. Okay, here's an example using lithium and fluorine, right? We sublimate the solid lithium, then we ionize it. See, there's my arrow. Sublimate it, ionize it, and this is the amount of energy we have to put in. Remember, negative energy is, let's see. No, that's not negative. I'm sorry. That's a mistake. That's not a negative. That's just a dash. So we have to put energy in. It's a positive 161. This one's a positive 520. And this one is dissociation of fluorine. Got to put energy in. It's a positive 77 kilojoules. And then we get some energy back. Now that is a negative sign for negative 328 because we're getting energy back. It's exothermic. And then here's the huge payback with lattice energy when the lithium ion and the fluorine ions come together for the solid. Okay, and there's your energy flow diagram to go with it. This is the calculation, right? So I was right. These are positive input, 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 get some back, get a whole lot back. And here's the overall. So this reaction is exothermic. Overall reaction is exothermic. So now we're going to switch gears a little bit and actually go back to a topic I introduced earlier, ionic character. Typically, every bond, every covalent bond that forms every bond that forms has some ionic character and some covalent character. There are no bonds that reach 100% ionic character. There's always a little bit of sharing in there. How do we know that? Well, in order to determine the percent ionic character, we measure the dipole moment of the bond itself. So if we measure the dipole moment of X with Y, we get a value, and then we calculate the dipole moment of X plus and Y minus. And that would be Coulomb's equation. Then we ratio those two and multiply times 100, and that gives you a percent ionic character. And then we can take those binary compounds and put them on a graph where you have percent ionic character increasing here and electronegativity difference between the two atoms on the bottom one. So the greater the difference, the higher the ionic character. But notice lithium and fluorine are the most ionic here, and they're not 100% ionic character. That just illustrates the point is all. Any compound that conducts electric current when it's melted is considered an ionic compound. So this is another one of those operational definitions. Why does the solid ionic compound have to be melted? Think of solids. What is a solid? Whatever it is. The atoms, the ions are packed in here and they're locked in place. So if it's an ionic compound, it'd be like that, right? And they're locked in place in that ionic crystal lattice. Well, if you try to pass a current through them, how's it going to get through there, right? If you bring in a positive charge here and a negative here, and there's your battery, then how are you going to get that flow through there? The current will not flow unless those ions move. If they're solid, if they're locked in place, they can't move. So, for instance, solid sodium chloride is an electrical insulator. So that's why you have to melt them. If you melt them now, turn it into a liquid, then these ions are free to move, and it will conduct electricity. That's the operational definition of an ionic compound. You have to melt it and then pass a current through it. If it goes, fine. If it doesn't, it's not ionic. So if you have solid sugar, right, table sugar, and you melt it, which you can do, it will not conduct electricity because the sugar molecules are not ionic. They will not transmit a charge. Okay, so let's get a little bit of theoretical here, which means we're going to have a theory, plus we're going to have a model to go along with it. And remember, well, we're going to talk about the characteristics of model, refresh your memory, or impose new information, whichever the case may be. A model in the sciences is an attempt to explain how this process works in reality. So a model, the first rule is a model is not reality. A model is an attempt to, a microscopic picture, so to speak, that you create that tries to explain the macroscopic behavior of the system. So that's your first rule. Models are not reality. Think of a model airplane, right? Well, or battleship. Well, that's for boys. Little boys do that stuff. I don't know how girls, maybe you have a model house, like a playhouse with your dolls and stuff. I know that sounds sexist, doesn't it? Well, when I was a kid, that's the way things were. Anyway, the model is not reality. The model is a representation of reality. So as a consequence, the model has to be simpler than reality, right? There are too many factors in reality that we can't track and we don't know. So we try to pick out the major factors and build our model with the major factors. And maybe later on, we'll throw some other stuff in there. I'll talk about that in a second also. So the model's not reality. It's an oversimplification. And over time, we add factors in. As a general rule, the model becomes modified with age and becomes more complicated. There are also several, in most cases, several assumptions that have to be made about the model in order for it to function. You have to assume certain things. And we're not going to dwell on that right now. It's just, that's the truth. Now, when a model is wrong, right, when the model does not predict the behavior that is witnessed in reality, doesn't mean that the model is useless. It can be used to explain that since our model didn't work, then we're barking up the wrong tree, so to speak, or we're chasing rabbits down the wrong hole. And you can go back and change it or start a new model, whatever is required to get closer to reality, to try to explain reality. So I may have said something about this before. Is the next slide? Yeah. What do we do when a model stops working? Right. Even if I've explained this before, it bears repeating. When a model stops working, when it won't predict behaviors of a system accurately, what do you do with it? Well, one thing you can do is restrict its application. Say, all right, this version of reality works for the model. The model predicts behaviors for this, but if certain factors change in the system, the model doesn't work anymore. So we don't use them over there. We have to define what those changes are in order to restrict the use of the model. That's one possibility. The other possibility is, well, and here's an example, Newton's laws of motion, also known as classical physics. Newton's laws of motion work fine in this range of masses. If you get too big, you have to change your model, and then we go to relativity. If you get too small, then Newton's laws stop working, and now we have to go to quantum mechanics. Or you can modify the model. Some have gone to really ridiculous levels. There's this effort that's been going on for decades to find a grand unifying theory of the universe, to bring all of the observed behaviors in the universe together in one grand theory. Well, part of that process has been to create models and introduce more dimensions to the models, to space, than we grew up with, right? Height, width, depth, and time. Those are the only ones that I can wrap my mind around. But these theoretical physicists, when I was a kid, they had like 11, 12, or 13 dimensions that they had added into their models. Now they're up to 26 or greater. That just goes from the sublime to the ridiculous. Maybe as a last resort, particularly if you have a lot of energy, time, and money invested in your model, you don't want to go to this third option. But sometimes you have no choice. Sometimes the model doesn't work ever. There's nothing you can do to fix it. Throw it out. A perfect example is J.J. Thomson's plum pudding model of the atom, right? Remember that one, where you have the atom is just this big conglomeration of a positive charge, and you have sprinkled in it negative charges, electrons. Well, Ernest Rutherford, with one simple experiment, the gold foil experiment, disproved J.J. Thomson's plum pudding model, and they just had to throw it away. It was no good. Okay, so when we talk about a bond energy, what does that mean? It actually means how much energy do you have to put in to break the bond? Okay, or how much energy is released when the bond forms from the free atoms, right? One is an endothermic process and one is an exothermic process. Now, when we draw bonds between atoms, the single bond represents 2 electrons. That's 2 electrons. You always have to have 2 electrons to form a bond. If you have a double, that means 2 more electrons. And if you have a triple, that means 2 more electrons. Okay, so you have 3 pairs of electrons for a triple bond, or 6 electrons. Now, one characteristic we have noticed about these bonds is single bonds are of a certain average length. Double bonds bring the atoms closer together. Triple bonds bring them even closer. Now, this is not a linear progression. In other words, the double bond isn't half the distance of the single bond. It's just shorter. And the triple bond is not a third the distance of the single bond. It's just shorter than a double bond. Now, a lot of work has gone into putting this chart together. And this defines the amount of energy that has to go in. Since these are all positives, we have to assume that this is the amount of energy in, I think it's kilojoules. Don't hold me to that, because there are no values given to it. Amount of energy, I know it's in joules. It's either joules or kilojoules per mole of the bond. So it's probably kilojoules. The amount of energy that goes in to break that bond. Okay, we've got single bonds over here. We've got some double bonds and triple bonds over here. Right now, why are we doing this? We're doing it because we can use these bond energies to calculate the enthalpy of a chemical reaction. All we have to know is how many of what types of bonds, and we can calculate what the expected enthalpy of that reaction will be. I know in previous chapters, we got at unknown or target reactions by combining information from other reactions using Hess's law. Now we can actually go down to the bond level with this information and predict very accurately whether the chemical reaction is exothermic or endothermic, and how much energy is required or given up. Let's see. So here's the formula. The enthalpy can be calculated. First, you add up all the bonds that are broken, the energy that goes into breaking the bonds of the reactants. And then you subtract the amount of energy that goes in, or that actually comes back from the bonds that form. So the reason it's written this way is because the values are given as positive values. That is the energy required to break the bonds. So if you put that energy in on the product side, you're forming bonds. So they need to all be converted to negatives. That's why the negative is here. So this letter is the capital Greek letter sigma. And in mathematics, it always means summation. You add up the values. D is the bond energy per mole of bonds. And it's always positive, like in our chart. And N is the moles of a particular bond. So let's see, I think we're going to have an example that we can work from. Yeah. Okay, so here's an example. This is a very, very simple one. And I'm not even going to draw it on the board. Notice, maybe I better draw it, because it's using a convention that we haven't described yet. When you see this, like that, that's derived from organic chemistry. And then you have this over here, and then that. This is easy to tell. This is a nitrogen-carbon triple bond. But what do you do with this? Well, by convention, the nitrogen and the carbon are bound together like that, and the hydrogens are like this. Okay, then you have your triple bond carbon. So that's what that one means. And then the other one is like this, only now it's bound to carbon and then triple bonded to nitrogen. And those are both gases. Okay, so we would say, all right, we have 3 carbon-hydrogen bonds at 413 kilojoules per mole. So I was right, it's kilojoules. And then we have 1 carbon-nitrogen single bond at 305 kilojoules. And we have 3 of these, so it's 3 times 413. And this is 1 times 305. And this is 1 times 891. Okay? And then we subtract 3 times 413 and 1 times 347 and 1 times 891. Okay, we can simplify this process really easily. Notice, if you break these 3 bonds right here, they're still over here, right? So that's a, as we say, that's a wash. You don't even have to consider those in the calculation. So what other bonds are the same? Well, the nitrogen carbon triple bond is the same on both sides. So it's a wash. So really, the only one we need to consider is this one and that one. So we take this one, 1 times the carbon nitrogen bond, 305 kilojoules times 1, and then subtract carbon-carbon, 347. All right, so what do we get? We get 2. We get negative 42 kilojoules per mole. Okay? Now, if you have a bunch of different bonds, or if the molecules are really complex, you may want to be methodical about it and just do it. But when we can make it simpler, I always do that. Negative 42 kilojoules. Okay? So we could have actually run the reaction and measured it, or we could have got Hess's law and had 2 or more equations with their enthalpies and done our magic like we've done in previous chapters, or we can do it this way. And this is extremely accurate. If you actually measure this reaction, you'll get very close to minus 42 kilojoules. It's surprising. Okay. This slide is for those classes that that are short, like hour and, let's see, hour and a quarter. So I have to split the lecture. But since we're here on one day and one day only, right, we're going to get the whole thing. So we're going to skip this slide and move on. All right. Okay, so we talked about, we introduced the concept of a model first. And the reason for that is we're going to use a model. It's based upon a theory. All models have to come with a theory. So this particular model, the localized electron model, is derived from the valence bond theory. So the valence bond theory simply says that bonds form between 2 atoms by an overlap of their orbitals. So the orbitals still belong to those atoms, but the electron orbitals are derived from the atoms, but they overlap when they share electrons, and that overlap is what forms the bond. So the valence bond theory is based upon only the valence orbitals. Okay, the core orbitals do not enter in. Those electrons are wholly owned by the atom and not shared in any way with its neighbors. just the valence electrons. So this little picture is I think these are probably p orbitals. This one atom and this other atom come close enough together. So we overlap that one and we overlap this one, we get something that looks like this. So this is a probability expression of now with the bonded atoms, where do the atoms reside? I mean, where do the electrons reside, right? In that space that's described by this banana here and this banana here. Okay. So the localized electron model then says, all right, if we're gonna bond by sharing these covalent, if we're going to form a covalent bond by sharing these electrons, these valence electrons, and the orbitals are overlap, then we need to say something about what are the electrons doing? Where are they found? What influence do they have on the polarity of the bonds and the geometry of the molecules? So the localized electron model simply says that, actually I was conflating both the valence bond theory and the localized electron model, because the localized electron model digs down, drills down and says, all right, these electrons and their orbitals still belong to each of those atoms. They're localized, but they just cooperate to form the bond. This model was worked on and proposed by several people. Heitler and London, Fritz London. Is probably London dispersion forces are named after him. And Linus Pauling worked on it also. Okay, so when we look at the localized electron model and we draw our structures, we have two types of electrons: those that are in the bond and those that are not in the bond. And typically, the ones that are in the bond, well, absolutely, the ones that are in a bond are paired. Two electrons form the bond. And those that are not, the non-bonding electrons, they tend to pair also, but they're lone pairs. In other words, they stay with the atom. They're not shared. And I'm going to show you what that means in just a minute. Oh, by the way, those bonding pairs, they occupy a space between the atoms for which they're bonding. Sometimes they're on axis between the atoms, and sometimes they're off axis. Right? We'll talk more about that in the second semester. Okay, this just tells you that for this exam and with this material from chapter 8 and 9.1 and 9.3 in your book, we're only going to discuss part 1 and part 2. Part 1, we're going to introduce a way of drawing those valence electrons around the symbol for the atom in such a way that it helps us form compounds and make some sense about the reactivity and where the bonds form and how many they form. That's called a Lewis dot structure. Then we're going to take that information in part 2 and predict their geometry using the Lewis dot structure and a new model, the VSEPR model. And I'll tell you what that means in just a minute. Part 3, we're going to save for the next exam, the last exam. In that case, we're going to introduce modifications to the valence bond theory. And then we're going to throw the valence bond theory out and introduce a new theory. Well, we don't really throw it out. We say, all right, it works for many cases, but the new theory, molecular orbital theory, works best for all cases. It's just a little more tedious to work with. And if you're not a chemistry major, we're not going to dig too deep into it because I'm not a chemistry major. So I can give you like a reader's guide version condensed version. Okay, so we're going to do part 1 and 2 now. Right, G.N. Lewis. He was an American chemist, and he was working with compounds that he knew were covalently bound. And he had this idea that only the valence electrons were involved in the bonding, right? The valence bond theory. And that there were only so many valence electrons available. And he noticed this concept that we introduced earlier, that what they were trending toward to form the bond was noble gas configurations. And he thought to himself, well, for the second period and the third period, that trend led to an octet of electrons. So he said, if you've got an atom here and it's got 8 electrons around it, like that, it's complete, right? It looks like a noble gas atom, right? So he used that concept, and you can draw these types of dot configurations for all the elements. Well, we're going to confine ourselves to the second, third, and maybe a few of the fourth period, and draw the Lewis dot structure for the atoms. Then we're going to put them together in the compounds and draw the Lewis dot structure for the compound. And then we're going to use that information to say something about the geometry. That's where we're headed. All right. So we mentioned the octet rule, but for hydrogen, the duet rule is the rule, because it doesn't have room for 8 electrons. So it shows an overlap of orbitals in a schematic form, and the 2 electrons in between the hydrogens that form the bond, right? So there's a single bond there. 1 electron from one hydrogen, 1 from the other. We get a dihydrogen molecule. For the fluorine, we also get a single bond, 2 electrons between them. But since fluorine has so many more protons and electrons to go with it, it looks like that, right? So if this fluorine, if we count the electrons around the fluorine, we got 8. We count the electrons around that one, we got 8. Now, we didn't create electrons, right? There are not 8 independent electrons around that fluorine or 8 around that one. The only reason they can count them is because they're in the bond. Fluorine still has 7 valence electrons because it's a halogen. But since it shares 1 from the other one, it thinks it has 8, right? Right. I'm anthropomorphizing atoms. All right, that's the octet rule. So there's your single bond with a single dash. There are double bonds. 2 dashes means what? Now, how do you write a Lewis structure? Those are the rules, and I'll leave them up there a little while. Oops, I'm getting the message, the internet connection is unstable. Why am I not surprised? To write the Lewis dot structure for an atom is very simple. All you need to know is how many valence electrons are assigned to that atom. And if you use the periodic table properly, you just walk your way over from left to right. Right? If you're looking for carbon is 4 positions from the left: lithium, beryllium, boron, carbon. 4 positions, 4 valence electrons. And if you're using the old style periodic table, there'll be a Roman numeral 4 above the carbon. That's why I like the old system. sometimes. Nitrogen is 5 positions over. It has 5 valence electrons. So we write nitrogen like this, only the valence electrons, 1, 2, 3, 4, 5. It has 1 pair and then 3 separate electrons. Okay, now what do you do if you got a molecule and you want to write the Lewis dot structure for it? The example here is water. You know this compound exists, right? In the beginning, you just have to know it is given to you, it exists. All right, now let's do something with it. What you do is you add up the valence electrons for all the atoms in the molecule. Right? You got 1 for each hydrogen. That means 2. And oxygen is in the 6th position, so it has 6. So we have 8 valence electrons to put into this model of oxygen and hydrogen, water. So the next thing you do is you got to decide for the simpler molecules, which one's in the middle, which one's the central atom. Well, in this case, it's easy because hydrogen can only form 1 bond. We can't put hydrogen in the middle because it can't form 2 bonds. So oxygen goes in the middle. And we form a bond with one of the hydrogens and another bond with the other hydrogen. Okay? Then you count up the electrons that you just used. 2, 4. Minus 4 equals 4 electrons. Now you start working from the outside in. You sort of go in a merry-go-round and you place these electrons. Well, hydrogen's got all it can hold. It can't hold anymore. So the rest of these electrons have to go in to the oxygen. 1, 2, 3, 4. Okay? That is a valid Lewis dot structure for water. All right, what that didn't show you, and on a subsequent slide it will, that didn't show you the lone pair electrons. These are lone pair electrons, non-bonding. These are bonding pairs. Okay. All right. Examples. We just did water. How about phosphorus tribromide? All right. Where's phosphorus on the periodic table? It's 5 positions over. It's in the same family as nitrogen. So it has 5 electrons. Bromine is a halogen. So how many does it have? It's 7 positions over. So each one of these has 7 electrons times 3. Right? And it wouldn't be balanced if we put bromine in the center and then a phosphorus out here and 2 other bromines. But also, the central atom is usually the less electronegative atom. So phosphorus is to the left and above bromine. So it's going to be the least electronegative. The phosphorus goes in the middle. Then we make our bonds. Okay. So that's 2, 4, 6. Minus 6 equals 20 electrons left. Now we go round and round and we place electrons on the outer atoms until they get their octets. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, right? So minus 18 means we have 2 electrons left over. those two electrons have to go inward to the phosphorus. So that's a valid Lewis dot structure for phosphorus tribromide. And then to be sure, sometimes you may want to go in and say, all right, let's count them up again. Right? Let's see. If this is an octet right here, that means 3 times 8 is 24, 25, 26. Got 26 electrons. All right, what's another one? Oh, hydrogen cyanide. All right, hydrogen's got 1 electron, carbon's got 4, nitrogen's got 5. So we got 10 electrons. All right, which one goes? With nitrogen, we make a bond with hydrogen. All right, so that's 4. 6 electrons left. Where do they go? Well, we have to start from the outside. Hydrogen's already got 2, so we can't do that one. So we put the 6 electrons here. Now nitrogen has an octet, but carbon doesn't. Carbon's only got 4 electrons. So how do you move those electrons around? Because that's it. We're done. How do you move those electrons around so that you don't rob nitrogen of its octet, but you give carbon its octet? You make another bond. You take a lone pair and make a bond, right? Take this one, and you take this one. Now you have this, right? 2, 4, 6, 8, 2, 4, 6, 8, 2. That's a valid Lewis dot structure for hydrogen cyanide. Okay, there's our water. There's our phosphorus tribromide. And there's our hydrogen cyanide. This depiction of water is alluding to the structure that we're going to deduce using the VSEPR model. So all right, so let's do ammonia. So there's ammonia. Count up the electrons. There's 5 for nitrogen and 3 times 1 for hydrogen, which means 8 electrons. So I put nitrogen in the middle, hydrogen out here, so that's 6 minus 6 equals 2. Got 2 electrons left, they have to go here. That's your valid Lewis dot structure. For ammonia. Let's see, let's do carbon dioxide. All right, 4 for carbon, 6 each for oxygen, so that's 12, 16 electrons. So carbon's in the middle because it's lower electronegativity than oxygen. There, there, and there. Okay, so that's 4. We have 12 electrons left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? So we used up all of our electrons. But we're in the same boat we were before. Carbon doesn't have an octet. So we have 2 choices. We can do this and this over here like that and like that and make this molecule. Okay. That's unbalanced. And in a few minutes, I'm going to show you how to break the tie. So we've got this possibility. Right? Or we could go this way and just do 1 from that side and 1 pair from this side. And that makes a double bond here, double bond there, and leaves 2 lone pairs around each oxygen. Okay. Like I said, I'm going to show you in a minute that this one is preferred. I mean, aesthetically, it's better than this one, but there's a quantitative way to approach this problem. Carbon tetrachloride is just carbon with 4 chlorines around it and complete the octet. That's no big deal. I'll let you do that one on your own. Especially since we waited a half hour for the internet to come back. All right. Now, like I've said before, nature just does what it does. And we've got to explain why, or explain how, or do something with it. Nature's going to go on its merry way doing whatever it wants. This compound does exist, boron trihydride. Right? So if we try to draw a Lewis dot structure for this, we see the boron's only got 3 electrons, and these hydrogens have 3 total, so that's 6 electrons. If we draw the structure, they're all used up. Boron cannot have an octet, but it exists. So that's it. That's the best we can do. It is deficient in electrons. This happens with boron. It happens with beryllium too, the next one to the left of boron. All right. We can go the other way. We'll take one of these examples. How about sulfur tetrafluoride? Right. Sulfur, it's in the chalcogens, oxygen family, so it has 6. Each one of these has 7. 4 times 7. So 28 and 6 is what? 34? Sulfur in the middle. Fluorine, 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 fluorine. Okay. 2, 4, 6, 8. 26 electrons left. All right. If we complete the octet for all the fluorines, that would be 2, 4, 6. 6 times 4 is 24. All right. That means we have 2 electrons left over. They have to go on the sulfur. Now we see that sulfur's got 2, 4, 6, 8, 10 electrons. Right? It exceeds the octet. And it exists. So we know that that molecule is right. It's just that this Lewis dot structure method forces us to put more than 8 electrons on that sulfur. I'm not going to do those. Well, there you go. Now, boron trifluoride is going to we can make an octet with that one because fluorine has a bunch of extra electrons. Right? Phosphorus pentachloride exceeds the octet. And sulfur hexafluoride also exceeds the octet. Now, this is just review. Second row elements never exceed the octet rule. That is, second period elements. Third period elements, sometimes they do exceed the octet. sulfur, phosphorus, we've had examples of those. How do we explain that? Well, the explanation involves d orbitals. Right? When n equals 3, you're in the third period, you notice that you have access to 0, 1, and 2, s, p, and d. So those unused d orbitals for those elements that have shown us excess electrons, greater than octet, make use of the d orbitals. Right? Those electrons have to go somewhere, right? And there's no room in the p orbitals anymore. So they have to go into the d orbitals. That's the way we rationalize the excess octets. Now there's another problem. This illustrates the case where we have Lewis dot structures that are valid, but we have more than one. And this nitrate ion is a perfect example. And notice when we have that negative, we have to add electrons. Right? There's one here. So nitrogen is 5. 3 times 6 is 18, which would be 23. But there's an extra electron on this polyatomic ion. So this becomes 24. And when you write the Lewis dot structure, you have to put those brackets around it and show that there's another charge. If you don't, then you can't justify all of the electrons that you put into the structure. But what we see is that this oxygen could get the double bond to make nitrogen an octet. This one could, or this one could. This is one of the failings of the valence bond theory and the Lewis dot structure arrangement model, the model, because it produces equivalent Lewis dot structures. In other words, if you didn't know where they came from, they would all look the same. I mean, all you have to do is rotate one of them, it looks like the other one. But we know that the different oxygens were responsible for that double bond. Okay? So these are different representations. The problem is, as far as the Lewis model goes, they're all equivalent. So this is where we have to tweak the model. And somebody, let's see, does it say that Linus Pauling did it? Yeah, Linus Pauling proposed resonance. In other words, we don't know which one is which. So we just say that they all exist, but they resonate backwards and forwards amongst themselves. And that way we can write the Lewis dot structure with our convention and say that these all three exist at the same time, and they just bounce back and forth. Now, in reality, this molecule, like that, has its oxygens. Now, I'm not going to write the lone pairs on there. These bonds are kind of in between single and double bonds. We know that because when you measure the length of the bonds, they're all the same. And if one of them was a double, then it would be shorter. So resonance can explain that because they're saying maybe it happens so fast that our equipment can't measure the difference. But the other explanation is this is the reality, right? We have partial double bond around each one. And the Lewis dot structure and the theory that goes with it is not adequate to explain it, right? That's just a failing of the theory. Now, it still works in many cases, so we keep using it. All right. there's another concept that we'll run into. I think yes, I believe we do get into it in the last, in your book from 9.4 to the end of the chapter. We get into a discussion of delocalization. Electrons, and here again, we're invoking that concept of lower energy means more stable. So when we delocalize these electrons from that one double bond and spread them over the other two bonds so they all look alike, that delocalization stabilizes the molecule. All right, let's see. We could draw these, but I'm not going to. I want to go on to formal charge. Remember when we had this possibility, this like that? Yeah, like that. Or this one. Right. How do you tell the difference? Because on the surface, they look like they're both valid Lewis dot structures. Well, well, that's not an organic compound, but we're going to borrow a concept from organic chemistry. At least that's where I first learned of it. It's called the formal charge. It's similar to oxidation state, but not quite. It's a bookkeeping scheme, and it works better for covalently bound molecules than for ionic compounds like oxidation state does. Oxidation state can also be used for covalent compounds, but it's not as useful for this type of operation. So what do we got to do? Well, we're going to say the formal charge is like a charge, but it's not really a charge. It just gives us a way, a handle on where the electrons are. And what we're aiming for is a molecule where the formal charges are minimized towards zero. We may not always get there, but if all the atoms are calculated to be a formal charge of zero, then that's the preferred formula. Okay, so how do we do it? The formal charge on any atom in a molecule is the number of valence electrons on the free atom. So the number of valence electrons here would be 6. The number here would be 4. The number here would be 6. Same on both sides. 6, 4, 6. That's the number of valence electrons if the atom were free. Now, how many electrons do we assign to that atom in the molecule? And here's how we do it. We say, all right, if there are any lone pairs or free electrons, those go all the way. They're assigned to that atom and none other. So this one has 2 free electrons. 4, excuse me, 2 pair, 4 electrons. And for any bonds, it gets half of the bond. So that's 1, 2, 3, 4, 5, 6. All right. This one gets 1, 2, 3, 4, half of those bonds. And same thing over here. And we subtract those values from the free atom valence electrons. 0, 0, 0. Right? So that says this is probably the best one. What would it look like on the other molecule? Well, this one has what? 1, 2, 3, 4, 5. Minus 5, which is plus 1. And this one has 1, 2, 3, 4. Minus 4, this one's 0. This one has 1, 2, 3, 4, 5, 6, 7. Minus 7. Minus 1 formal charge. That's why this one is preferred over that one, using this method. So you always start with the valence electrons for the free atom, and then you count up and subtract the electrons that are assigned to that atom in the molecule. That's the formal charge. Okay, those are just rules. Okay, consider this structure, POCl3. Assign the formal charge for each atom in the molecule. All right, and they've kindly already written the Lewis dot structure for us. Let's see, P, O, and then Cl. Right? Everybody's got an octet. All right. 2, 1, 2, 1, 2. Right? 2, 1, 2, 2, 2, 2, 2, 2, 2. Okay. So let's start with the phosphorus. What's the valence, number of valence electrons for phosphorus? It's in the 5th row column over. So it's 5 electrons. So this one has 5 minus 1, 2, 3, 4. Plus 1. So phosphorus has a plus 1 formal charge. How about oxygen? Well, oxygen has 6. So we subtract 1, 2, 3, 4, 5, 6, 7. Minus 7. It's minus 1. And chlorines are all alike, so we only need to calculate one of them. So chlorine starts out with 7. And we got 1, 2, 3, 4, 5, 6, 7. Chlorines are all 0. Okay. And there and there. Those are the formal charges for each of the atoms in that molecule. One thing that has to be true, when you add up these formal charges, right? These are all going to be 0, 0, 0, 0. So 0, 0, 0 is 0. And plus 1 and minus 1 together equals 0. If it's a neutral molecule, they've got to add to 0. If it's a polyatomic like that nitrate with a charge, then they have to add up to the charge. That's similar to oxidation states, right? You have to add them all up. If the molecule is neutral, then they all add up to 0. If it's a polyatomic ion, then all the oxidation states add up to the charge. And here are non-equivalent Lewis structures like we drew before. And I kind of jumped ahead of things. And this model of carbon dioxide is preferred because the formal charges are all 0s. Okay. Formal charges provide estimates of charge. They're not real charge. I see it as a bookkeeping scheme. So just don't take this method or this model, this theory, don't take it where it shouldn't go. That's the thing. Just use it where we've shown you that you can use it to break ties between valid Lewis dot structures. All right, now we're going to get to geometry. Once you've chosen a valid Lewis dot structure that is the preferred for a given molecule, then you got to say something about its geometry, because it's simple enough to determine the dipole moment for a bond, but you need to know the geometry before you can assess the dipole moment of the molecule. So this VSEPR model is the way we do it, at least with the valence bond theory. VSEPR stands for valence shell electron pair repulsion. VSEPR. The electron pair is the part that digs at me, because we treat single bonds, triple bonds, double bonds all the same when we do our assessment and assign geometry. So I would think valence shell electron group repulsion. It's based upon a very simple concept. when you have a central atom and you have various X, Y, Z, maybe there's another Y here and maybe another Z over here. When you position these around a central atom, these molecules are, and it could be another lone pair like this. When you position them around that central atom, they move, because they're all negatives, they move to repel each other to a position where the repulsive forces are minimized. That is, they get as far away from each other as they can, and that speaks to regular geometries, right? If there are only three, like this one that we looked at earlier, the farthest they can get from one another is a trigonal planar, we call it. It's a triangle in one plane. Okay, the repulsion is the key. And of course, the valence electrons are responsible, and you don't mess with the core, just as always. All right, now we're going to try to stick with either single central atoms, molecules, or maybe two or three molecules that have two or three central atoms. You can determine the geometry around a central atom in different parts of the same molecule, right? You just have to focus on that one central atom and what is it connected to. And you can have different geometries at different central atoms in the same molecule. That's what that last statement says. All right. So this three-dimensional arrangement, if the structure is linear, like carbon dioxide, bond angle is 180 degrees. I showed you these earlier, so I'm not going to linger here too long. I'd rather build a table that you can use. Trigonal planar is like the one I just showed you here. Bond angle is 120 degrees. 4, tetrahedral, 109.5 degree angle. And there are more that we're going to show you. Okay, so how do we use the model? These are the instructions. But I'm going to, in a nutshell, you count the number of groups around the central atom. If it's a single bond, one group. If it's a double bond, one group. So it doesn't matter if it's single or a double. And then, in this case, it'd be 1, 2, 3, 4. And then you apply those 4 groups to the regular geometry that is assigned to them. That gives you the electronic geometry, because sometimes you have lone pairs in there. If you want the molecular geometry, which we usually do, then you just cover up the lone pairs and say what's left over, right? In this case, 4 groups means tetrahedral. But if we cover that up, then we get X in the middle, and we get our tetrahedron right here. And say we have, I don't know, a Z in the back here, and a Z over here, and a Y over here, and a lone pair up there. If you cover up that lone pair, what do you have left? You have a trigonal pyramid, a triangular base with the central atom at the apex. That's the molecular geometry. But we have to do the electronic geometry first. Then we move to the molecular. Okay. So let me see. I thought we had a those are examples. I'd rather get to, yeah, here we go. So I'm going to build a table based upon this information that's given in the slides. The number of electron, actually they say electron pairs, I say groups, the number of groups. Yeah, I need another marker. Okay, the number of groups over here. Then we have the electronic arrangement, or the electronic geometry. Then we have the molecular geometry. Okay. That was not working either. Hold on a second. Let's try this one. Okay. So if you have two groups around the central atom, we don't go for one group, because what if you have one group? Right? Only two atoms? It's got to be linear. There's no other choice. So if we have two groups, then the electronic geometry would be linear. That gets the groups as far apart from each other as possible, and our example is carbon dioxide. So if there are atoms occupying those positions, the molecular geometry is still linear. If one of them is a lone pair, you're still linear, right? So one lone pair means linear. How about three groups? Three groups gives an electronic geometry of trigonal planar. Okay. Now, if you have two lone pairs, one lone pair, one lone pair, and of course, if they're all atomic, then that's the same, trigonal planar. If you have one lone pair, what do you have? You have a bent molecule, right? Just cover up the one, then you've only got, you cover up one of the three, if it's a lone pair, and then you got bent. That's what's left over. Some books call it angular. You have two lone pairs, then you're back to linear. Okay? And the angle here is going to be 120 degrees, right? Because that's the internal angle for this isosceles triangle. If you have four groups, right, we said that one already, the electronic geometry is tetrahedral. And if they're all atoms, that's tetrahedral, and the bond angle is 109.5. Okay, if you have one lone pair, what does that do? It does like ammonia. Cover up the lone pair, what do you have left? You have nitrogen and three hydrogens at the base of the pyramid. So this is a one lone pair means trigonal pyramid. If you have two lone pairs, now you have a bent molecule with the same angle. And if you have three lone pairs, it's linear, so I'm not going to put that one up there. Let's make room. Let's make room for five. If you have five groups around the central atom, the electronic structure then is trigonal bipyramid. Right? You have this triangle in the center, and then you have something up here and something down here. So there's your pyramid here, pyramid there. It's like Actually, it's like a tetrahedron on top and a tetrahedron on the bottom with their bases against each other. Trigonal bipyramid. Right? So that would be the molecular geometry if they're all atoms. If there's one missing, one lone pair of electrons, what does that do to the geometry? Well, typically, if you draw the there, and you have your trigonal bipyramid, where is that lone pair going to go? Typically, the lone pair sits here on the triangle, which means if you have an atom in the middle and you've got a bond here and a bond here and a bond here, a bond here, these two form the base of a seesaw. So you got an atom here, you got an atom here, an atom here, an atom here, and you got your central atom there. This is called a seesaw. It's got one, let's see, 1, 2, 3, 4. Yeah, 4 out of the 5 are atoms. It gives you a seesaw molecular structure. If you're missing 2, then that means that there's a lone pair there. And what you have is, this one goes away. Now you have a T shape. Right? And if you're missing 3, that would come from here also, and then you're linear. 3 lone pairs yields linear. Now, I'm not just making this up. These structures, there are examples of molecules that have been analyzed and found to occupy these shapes. Now, don't ask me how they did it. It's probably time consuming and very expensive. But this is the way it actually goes. We just have to explain it. Now, the last one I'm going to do is 6 groups. 6 groups is octahedron. An octahedron is like a trigonal bipyramid, only instead of a triangle here, it's got a square. It goes up to there like that. It goes down here like this. And if you look at all the sides, you got 4 sides on the top and 4 sides on the bottom. Octahedron. 4 plus 4 is 8. All right. So that would be an octahedral molecular geometry, unless you have one lone pair. And the lone pair on this design usually occupies one of the apexes, which means if you cover that up, you're left with a square pyramid, just like the pyramids of Egypt. Square pyramid. Okay. If you're missing 2, if you got 2 lone pairs, the other lone pair is usually at the other apex. So that means you have square planar molecular geometry. Okay. If you're missing 3, I'm not sure where we're going with that one. I don't think that's covered in this course, right? It's probably too complicated and it's not definitive, right? But these are fairly definitive the way they are, right? So you have examples here. There's your octahedron. And here's what happens with a tetrahedron when you remove one of the positions is a lone pair. 2 positions is a lone pair is bent. Now, the interesting thing is the bond angle in a tetrahedron is 109.5 degrees. If all of the positions are occupied with atoms. if they're not occupied with atoms, like ammonia, then the bond angle is less than 109.5. Why? Because you got this lone pair up here, and when a lone pair obviously is not in a bond, it tends to balloon, right? So it puts pressure on these other bonding electrons and squeezes them down to where the bond angle is it's less than 109.5, maybe close to 108 degrees. But the reason it's that way is because those ballooning lone pair compresses the others. Water's even worse. It's a bent molecule with two lone pairs up here. So they're going to put even more pressure, and the bond angle in water is even less than that. Okay, let's see what else we got going for us. Okay, here we go with, there's trigonal bipyramid. One lone pair makes a seesaw, two lone pair makes a T-shape, and three lone pairs makes linear. All right, so we're not gonna beat this horse anymore. The octahedron, it's obviously more complex than we want to deal with in this course. But the sequence of events is draw your Lewis dot structure, then do the VSEPR and determine the electronic structure, then cover the lone pairs and see what's left for your molecular geometry. Okay, let's see. We ought to be getting pretty close to the end here. Let's see. Here's a problem. Actually, it tells you what happens under certain conditions with PCl5, phosphorus pentachloride. In the gaseous and the liquid states, the substance consists of PCl5 molecules. That's it, nothing else. But in the solid state, something strange happens. You get a 1-to-1 mixture of PCl4 plus and PCl6 minus ions in the solid. So the PCl5 goes away, and you're left with this cation-anion mixture in the solid form. What we want to look at is what are the geometries of these molecules. So we have the three. We have PCl5. We have the PCl4 plus. Yes, and the PCl6 minus. There we go. All right, let's do this one. Lewis dot structure. Phosphorus is 5. Chlorine is 7 times 5. So that's 35. That's 40 electrons, right? Okay. How about this one? Phosphorus is 5 again. 4 chlorines is 28. So 28 and 5 is what? 33. But look, we're missing 1. So it's actually 32. This one is 5 here, and 6 times 7 is 42, plus 5 is 47, 46, right? 42, 47, excuse me, and then 1 extra. So it's 48. Okay, now let's draw our structures. There's phosphorus, there's 5, 2, 3, 4, 5 chlorines. Okay. I want to look at the predicted geometries. Okay, that's as far as I'm going to go. I'm not going to put in the lone pairs around the ligands. We call them ligands of the chlorines. We don't need them. Okay, how about PCl4? Let's see, P, Cl, 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 Cl. Well, I'll tell you what, we probably should consider the lone pairs just to be sure that we've got all of our electrons counted for. So around this chlorine, there's 2, 4, 6, 8. So 8 times 5 is 40. Right? We used up all the electrons. Okay, this one we've got 2, 4, 6, 8, 24 electrons. Okay, 2, 4, 6 times 4 is 24. Okay, so that uses up all of our electrons in this structure, but that makes it complete. How about PCl6? Okay, 1, 2, 3, 4, 5, 6. So it's 2, 4, 6, 8, 10, 12. Yep. 6, 3, 36 electrons. 1, 2, 3, 4, 5, 6. 6 times 6 is 36. So we used all those up. There are no lone pairs in any of these molecules. And this is a negative ion. Okay, what are the structures? Well, let's see, we've got 5 here around the central atom. That means what? Trigonal bipyramid. Okay, this is 4 around the central atom, which means what? Tetrahedral. And this one is 1, 2, 3, 4, 5, 6 around the central atom, which means octahedral. There you go. So what we have to do is, this is gas and liquid. This is solid. These two together in the solid. So they have to, this tetrahedral and octahedral shapes have to fit together somehow in that solid. And we'll have to wait till next semester to talk about that type of geometry. Okay, trigonal bipyramid for the PCl5. There we go. And the PCl4 plus gives us a tetrahedron. There we go. And the PCl6 gives us octahedron. Now, our last, I'm pretty sure this is the last discussion. For the longest time, chemists considered the noble gases to be inert because their S&P orbitals were completely filled. In fact, all of their valence shells were filled with electrons. They were not expected to be reactive at all. What was discovered was some of the larger ones, like krypton and xenon and radon, could be forced to form compounds, usually with one of the halogens. Fluorine is a common one. I think they've formed compounds with some chlorine also. But these compounds were synthesized, and then their geometries were elucidated by other methods. The one we're going to look at now is xenon tetrafluoride. Xenon tetrafluoride. So let's see if we can predict the geometry of xenon tetrafluoride and whether or not it is polar, whether it has a dipole moment. Okay, xenon has 8 valence electrons. Fluorine has 7 times 4. So 28 plus 8 is 36, right? 36. Okay, xenon in the middle, and fluorine, 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 Okay, 2, 4, 6, 8 equals 28 electrons. Okay, 6, right? 6 around each fluorine, which means 24 electrons are used up to make fluorine its octet. What did I say, 24? 6 times 4, yeah, 24. So we have 4 electrons left over. They have to go on xenon. Okay. Now, how about the geometry? Right. We know that these are going to be polar, right, toward the fluorine, right? Because fluorine is the most electronegativity the most electronegative atom or element in the periodic table. So the question of dipole moment depends on its geometry. Well, its geometry should be 1, 2, 3, 4, 5, 6. 6 groups. Which means what? Octahedron. That's the electronic geometry, right? So if we draw an octahedron, right, we put, where are we going to put everything? Right? Do we put 2 fluorines here and then a fluorine and a fluorine on the apexes? That would be unbalanced. What happens is the fluorines go on the square and the lone pairs go on the apex, the upper and lower apex. So now that we know the electronic geometry, what's the molecular geometry? We cover these up. What do you have? You have square planar. Each of these has a dipole that direction. And they all cancel each other out because they are equivalent. Right? So this molecule is non-polar, square planar. Okay? That's a fact. There you go, there you go, in the slide. And there you go, and there you go. Now, this slide considers various possibilities, right? If we go with this one, where the lone pairs are on the square, then the molecular geometry is seesaw. But that would mean that the molecule is polar because they're unbalanced. If the lone pairs are here at the apexes, then the molecule is square planar and it's nonpolar. And all you have to do is measure the polarity of the molecule, which can be done, and you find that it's nonpolar, which means the right-hand side, the B possibility, is the correct one. And the bond angles have to be 90 degrees, right? Because this is a square. That's 90, that's 90, that's 90, and that's 90. 4 times 90 is 360. Okay. There you go. Yeah, this just puts in black and white what I've been telling you. So I'm not going to labor this any further. And that's it for bonding, the general concepts. We're going to get into more specifics. We're going to review this the next time we meet and then have an exam. And then the final chapter in my book and your sections 9.4 to 9.8 cover modifications to the valence bond theory that make it a little more workable as is. And then we're going to move to the molecular orbital theory. That solves a lot of problems. Okay, so that's it. I'm going to stop the share.